So we were looking at this system, which is a second quantized system. Okay, I mean the description is second after second quantization, and it is equivalent to that of a collection of infinite number of non-interacting harmonic oscillators. Okay, so each sum represents a harmonic oscillator in this sum, and each oscillator has its own natural frequency. So here this is basically h bar omega n. So omega n is different for different oscillators. And we started looking at, if you recall, let me go back if I can. Okay, here we started looking at the eigenstates of this Hamiltonian, and that's what I'm going to do today. A little bit more generality. So let's find out the eigenstates of this Hamiltonian. Okay, and we found that if you take the vacuum, that's the ground state of your theory. Okay, you recall, if you act on this with the Hamiltonian, you get 0, or if you put a half h bar omega term here, then it gives a half h bar omega get 0. Okay, so that's the ground state, and it is also called vacuum. Okay, so a most general state, which will be an eigenstate of the Hamiltonian, would be of this form. So I take a n with the subscript capital N and dagger. Okay, and I act with several of them, a n2 dagger, a n1 dagger. Okay, and let me denote this system by, this state by the symbol. Sorry. Okay, so your n1 could be 1, n2 could be 2 or 5 or whatever, and so forth. Okay, and your capital N is basically telling how many daggers you have, or how many oscillators are. Okay, no, not really. Let's say a capital N denotes how many daggers you have put. How many daggers? How many A daggers you have? How many daggers are in the string? Okay, string meaning this string. Okay, this string of letters, how many of A daggers you have there. So that is what it is counting. So if you look at the action of Hamiltonian on this state, okay, you can easily compute the way we did last time. Okay, that it will turn out to be the following. So it will be of course an eigenstate, and the eigenvalue would be the sum of these energies. Okay, that's evident from the discussion of last time. Okay, a specific example of such a state could be that you take n1 to be 1, n2 to be 1, and capital N minus 1 to also be 1, and let's say this one is state number, oscillator number, corresponds to oscillator number 7. So you have a state 1, 1, 1, 7. So this is one of the eigenstates of the system, right? So you'll have here A1 dagger, so on and so forth, A1 dagger, and finally A7 dagger. Okay, so this is what it means. Okay, and if you have such a system, then of course the energy of this system would be, using the formula above, you can find that it will be just, let's say these are okay, I have already written capital N minus 1, so this will be capital N minus 1 times E1 plus E7. Okay, that's what you will get. Right? Okay, so that's fine. Now you can see that there is a special symmetry of these states which is obeyed because these are A daggers, and A daggers all commute with each other. Right? You remember the commutation relation? Let's go back and see if we can find it. Here, see, AM dagger is delta MN. Okay, and what is not written here, I thought I have already said here. No, not here also. Okay, let me check. Okay, so somehow I missed to write that. I can, the A daggers commute with themselves. Even for one particular oscillator, the A daggers commute, the A's also commute, and A dagger anyway, they do not commute. They commute only when they belong to different oscillators, right? So here, this is saying that A and A dagger commute if they belong to different oscillators. If N and M are different, then you get a 0 here, so they commute. Okay, the only issue is when they are from they belong to the same oscillator, the index M and N, then only they do not commute, and the A's and A daggers anyway commute. So I can write here AM dagger is equal to AM is equal to 0. Okay, you can put a hat. These are operators. This anyway holds true. Okay. Okay, so we can use that here. Where are we? Here. Okay. So all these are going to commute, right? Does not matter what is here. So if they are all going to commute, then we have a symmetry. Let me write that down. Okay. So if you take a state which is, some things are here, then you have NS, then you have NT. So it's the same kind of notation as before. I am just omitting what could be written here because I just want to, okay, let us make it a bit nicer. Okay. So this is what? This is corresponding to these dots. You have some A daggers, okay, and then you have A and S dagger corresponding to this NS, then you have A and T dagger corresponding to this NT, and then corresponding to those dots you have other A daggers acting on the vacuum of this theory. Okay. Now you see that because I can interchange these two, nothing changes because they commute. So this one will go through all the A daggers you have here because they commute and can come here, and this guy can go backwards because it commutes, it can sit here, there's no problem, which means that this state or all the eigenstates of the Hamiltonian, they are symmetric under exchange of NS with NT. Okay, so if you exchange these two, the result does not change. Okay, which is just saying that I can interchange these two positions. Okay, so I can say everything remains the same, and here I interchange NT and S That's what is the statement about the symmetry of the states of the system. Okay, that's good, and as you saw, the reason was that A daggers commute. Okay, A daggers commute. Okay, that's fine. Nice. And how about the symmetry? The normalization of these states. So if you are given a state which is an eigenstate of the Hamiltonian, so if you take a state, let me do a shorthand to avoid writing too much. So let's say ket alpha is some state which could be something like this. Okay, if that's a state of the Hamiltonian, then that's the state of that's the eigenstate of the Hamiltonian. Then C times ket alpha is also an eigenstate, right? And you would like to normalize the states, meaning fix the C such that if I call this as beta, or not beta, let's call it alpha prime, or let's call it alpha, alpha prime. So what I have to do is I have to fix C such that alpha prime, this inner product is 1. Okay, that is, when you do this, you call that these states are normalized. So I have to find C such that this happens. Okay, so let's look at normalization now. Okay. So let's look at this. Let's look at the state as we wrote before. The states, okay, N1 up to N. Okay, I'm looking at the normalization of these states. So okay, let's check. So let's see what I get for the inner product if I take the inner product of this ket with its corresponding bra. Okay, and let's see what we get. And depending on what we get, we can divide accordingly to get a normalized eigenstate. Okay, so let's do that and recall what this was. This was AN1 dagger, AN, okay, let me see, A and 2 dagger, so and so forth, A n minus 1 dagger, A n dagger acting on ket 0. Okay, so if I'm looking at inner product of this one, so first I should calculate this quantity, and that's easy. The ket turns into a bra, and because all these A daggers commute and correspondingly A's commute, I don't have to worry. I can write here, what should I write here? Let me check. And okay, this is how I want to write. I want to write it like this. A n n. Okay, that's what you can write. Now let's look at this inner product. So the inner product is so you write this one 0, an1, an subscript 2, an with a subscript n, and then you have a and subscript 1 dagger, an subscript 2 dagger, and an minus 1 dagger, an dagger ket 0. Okay, we are almost there. Okay, so yeah, let me write it like this: 0 and 1 up to a n minus 1. So you have a subscript n minus 1 here. That's the one I'm writing here. Now this guy, I'm going to push it through these a daggers. Okay. Now you can make these two commute. Okay. So, sorry, these two commute if n1 and n2 correspond to two different oscillators. So, if n1 is not same as n2, then they commute anyway. Sorry, I meant these two. Okay. Sorry for this mistake. So, what I'm trying to say is these two guys, the A and A daggers, they commute if this subscript is different from this subscript, right? Because the A daggers corresponding to different oscillators commute anyway. They do not commute, and you get a constant term if A and N and A and 1 dagger, they correspond to the same oscillator. So for the moment, let's take all the indices to be different. Okay, so take the case where N1 is not equal to N2, is not equal to N3, and none of them are equal. Okay, so I'm looking at a state where none of these are equal, okay, to avoid that complication in counting. Okay, good. So if none of them are equal, then this will commute with this, so it sits here then, but this commutes with this one also, so it can go through. It will go through up to here. Okay, so up to here it will be able to come. So let me write that down. So here, and then it will sit next to this term before this, because this cannot commute. They don't commute. So I have to use the commutation relation. So let me do it in steps. And then you have, I'm just writing in the next line for ease of visualization, AN1 dagger, AN2 dagger, AN subscript n minus 1 dagger, and then you have A and N and A n dagger. Sorry, this was A n, so this is n subscript n. Okay, so let me write that down in the next line. You have A n n, A n n dagger acting on the vacuum. Okay, good. But now here you can use the commutation relation, and this will be equal to n dagger A n. You remember, I want to bring this next to the ket because then it can annihilate it. So I'm using commutation relation, and then you get a +1. Okay, so this, let me write, this entire piece becomes this, which is just this, right? Because this guy kills the vacuum, and this one is left. Okay, so what I have effectively is AN1 to AN n minus 1, and then AN1 dagger up to AN n minus 1 dagger, and this gives me just a ket 0. Okay, so this is same as what you have here, right? Except for the fact that this term, this A and this A dagger, they are gone. Okay, so it's looking exactly the same. So you can repeat the same steps again and take the one here, AN n minus 1 dagger, and try to bring it next to it and do the same thing as we did here, and again you will pick up a factor of 1 here, this will kill, and you will be left with ket 0. Okay, so if you keep repeating that, you will end up with 1, right? Because let me do it in 2 steps. You will end up with this 0, and you know the last one will be what? AN1 dagger. This will be the last one which will be left, and then again the same step. You will have this, and if you say that my ket 0 is normalized, meaning this product is 1, then I got 1. Okay, which means that the state with which we started this one, this is already properly normalized, so I don't have to do anything. Okay. Now you can already imagine that if this is not true, if some of the n1s and n2s and n3s are same, then you have to take care of the commutation relations and you will get a normalization factor which will not be 1. So that will be left as an exercise. Okay. So exercise is find the normalization of the state. Let me denote the state by alpha. Okay, it's not a good notation, but I don't want to spend time writing all the indices, so I will use alpha. But the definition of the state is this. So you have a n1 dagger m1 times. So you have a n1 dagger, a n1 dagger, a n1 dagger. It appears m1 times. And you have a n subscript capital N, this thing appearing m subscript capital N times, and that's your vacuum. Okay. Now, of course, this is an eigenstate of the Hamiltonian, just as you saw before. Okay. And the goal is to find a C, a constant C, such that C times alpha, let's put a C here, okay, C times cat alpha. This is, let me define it to be alpha prime, so that this state alpha prime is a properly normalized state, meaning find C such that alpha prime is 1. Okay. This. So that's what you have to do. Find the normalization of the state, this one. Okay, now that I have put all the C's, it sounds strange, but you understand, right? You have to just find the C. Okay. So that will be an exercise. Okay, and in the next video, I will start looking at another system that will have states which will have one-to-one correspondence with the states that you have seen in this this theory. Okay, so that's what I'm going to do in the next video.